For the next several lectures, we're going to cover results in differentially private machine learning and statistics. But before we go into technical details, today's lecture will be a little bit more philosophical in nature. In particular, we're going to discuss today what is a privacy violation and what isn't a privacy violation. We'll see that these are generally aligned with what differential privacy can protect and what it cannot protect against. Via a series of examples, we're going to couch our expectations and try to understand what types of violations differential privacy can and cannot protect against. And misunderstanding this point is often a common pitfall, even in many published papers. Perhaps one of the misleading things is the fact that the word privacy in casual use is not exactly aligned with what differential privacy guarantees and the type of individual level privacy that we're going to try to protect. And indeed, under casual use of this term privacy, the type of privacy violations might not be the data analyst's responsibility to prevent, and in fact, instead the individual should be more careful with the other data that they reveal. There's a lot of stuff, it might be a bit confusing, but it'll all make sense with a number of examples, hopefully. So let's recall what differential privacy says. Informally, differential privacy implies that an algorithm's output will be similar when a single data point is modified, nothing more and nothing less. In particular, it doesn't prevent statistics and machine learning from working, and in particular, it doesn't prevent anything that they would imply as a byproduct. So whenever you're in doubt on whether or not differential privacy can protect against some alleged privacy violation in an analysis, ask yourself the following three questions. The first question is, would the answer truly be fundamentally different if a single data point was changed? You might see that this kind of aligned with differential privacy, and that's with a good reason in mind, because we really are going to consider what a privacy violation is when a single individual's data point is what really makes the difference here. So, if you change their data point, or it was something different, or it wasn't existent in the data set at all, if you would still get the same answer, then it's not really a privacy violation, since it somehow doesn't depend on the user's data. Sort of similarly, asking, is this just machine learning working as it's intended to be? Indeed, if machine learning is running on a data set and it doesn't depend too much on one data point and it sort of learns the underlying trend, that's kind of machine learning just doing what it's supposed to do. And so that isn't generally a privacy violation. However, even in these cases, you might be still thinking that, hey, something's wrong. Why, this was machine learning doing what it's supposed to do, but it still feels like there's some sort of privacy violation, perhaps in the casual sense of the word. It might be worthwhile investigating and thinking about at which point in the past was privacy given up and who gave up privacy. So these are some important questions that we'll ask in many settings. Let's just revisit the second point I made there. Is this just machine learning working as intended? Let's say another way of saying point two would be, consider your supposed privacy violation, the type of event that you're considering whether or not this is a privacy violation. Suppose this is synonymous with the learned predictor itself being accurate, then it's not a privacy violation. Just let me repeat that. If a privacy violation is the same as saying the classifier is accurate, or the model is accurate, then that is not a privacy violation. Think about it, because the only way that you could possibly avoid this type of situation where a privacy violation is synonymous with accuracy is to in fact output an inaccurate predictor, one that kind of gives up on trying to do something accurate for the sake of privacy. So this is easy to do, just output random guesses or something which is totally independent of the data. This is easy to do, but however, it will be useless. To quote a movie older than anyone in this class, myself included, the only winning move in this type of setting is to not play. So without getting too much into technical details, let's recall what a machine learning algorithm is. A machine learning algorithm takes as input a data set consisting of several data points, each of which has a feature vector and a label. In the differentially private setting, this data set is usually what we think of as the sensitive information. That is individuals' data, and we want to protect their privacy. The algorithm takes in this data set and it outputs a classifier. A classifier is an algorithm which takes in just a single feature vector and outputs a prediction of the label associated with that point. So under differential privacy, this is the object we wish to be differentially private. The classifier is supposed to be differentially private. They'll comment that there is some work in which we only require the predictions of the classifier to be private. The classifier's accuracy on this point is measured via some distance between the prediction and the true label, which is usually averaged over an entire test data set. Just to give you an example, suppose, just to make it concrete, let's say, suppose we want to train an image classifier which says whether a picture contains a cat or not a cat. So what we would do is typically we feed it in a bunch of different images, some of which are cats, which are labeled as being cats, and some are not pictures of cats, which are labeled correctly as not being cats. This would output an algorithm, a classifier, and this classifier would take in a single picture, and what it would do for each picture is tell us, is this a cat or not a cat? For this type of setting, we might use a lot, our measurement of the accuracy as how many of the pictures in some test set it gets correct. You know, how many of them, the cats that it correctly classifies as cats, and how many of the not cats it correctly says are not cats. So that's the basics of machine learning. And again, what are we thinking of our sensitive data set here in a differentially private setting? We would be thinking of the training data as being the sensitive data. That is the pictures of cats and not cats, which we feed in, and in particular, not necessarily the test data. When we say test a point, that's not necessarily a data point which we're trying to protect. Okay, so we have what a machine learning algorithm is, and let's do a very, very simple but rather contrived and kind of odd example in order to get across some of the key ideas behind what machine learning can do and what differential privacy and does not preclude. In particular, we're going to see what is not really a privacy violation. So let's suppose we had the following training data of feature and label pairs. So this is going to be the domain, the feature vector, they're just going to be a single number, and the label is just going to be a single number. So let's suppose this is our training data. We have the training data being the feature 0 and the label is 1. Okay, so we have 0, 1. Now let's suppose we also have the training point 1, 2. Okay, and we have, say, 2, 3. We have 5, 6. We have 11, 12. We have -6, -5. We have 0.5, 1.5. We have pi and pi plus 1. So maybe you're seeing the pattern here. In fact, just by inspecting this data, you'd be able to quickly deduce that the pattern is that the label y is equal to x plus 1. Indeed, every single data point matches this perfectly. So any sort of natural algorithm would be able to predict that this is the pattern. Okay, now suppose we were tasked with predicting the label of a point with x equals 4. This was a point which was not in our training data. Then this classifier would output the correct prediction of y equals 5. I think everyone would be comfortable with characterizing this as not a privacy violation for the training set. Indeed, this doesn't have anything to do with the training set at all. Yeah, the point was not in the training set. But instead, let's think about something else, a slightly different query. Suppose we were given the point x equals pi. Recall, our training data actually had the point pi, comma, pi plus 1. That was the feature label pair. And this appeared in the training data. Then the predictor, our classifier, would correctly predict that y is equal to pi plus 1. So now, is this a privacy violation? This is a tougher question because indeed, this was a point in our training data where it had, we had that we gave it the point x and it managed to correctly predict that y is equal to pi plus 1. And my claim is no, this isn't a privacy violation, though instantiations of this phenomenon, when we look at less contrived examples, instantiations of the phenomenon will seem kind of creepy, but this is kind of just science working as intended. In some sense, we didn't actually learn anything about this specific point. We learned something about, or we didn't learn anything private about the points in the training data themselves, but instead we learned something about nature. nature is really the relationship that y equals x plus 1. And we just applied that relationship about nature, which doesn't actually have anything to do with the training data, to this point x equals pi. Let's go down our checklist. The first thing to note is that the answer to this would not have been any different if the training data, if this data point was excluded from the training data at all. If you just left out pi plus 1, if you still have enough data points in the training data, then you would still have learned that y equals x plus 1. This kind of corresponds to, in differential privacy, how there's a very simple differentially private algorithm which would discover precisely this relationship y equals x plus 1. Specifically, you can consider any of the stability-based histogram approaches that we mentioned in 2 lectures ago, and that would be able to do this with a very low cost for privacy. But again, that's not really the focus of today. The point is more that, what am I trying to get across here? The fact that this data point, this one specific data point, was not really crucial to arriving at the final classifier that we got. So all we saw here going on was just a very rudimentary form of machine learning in action. If this still feels wrong to you, if you still feel like something bad happened and we somehow found out data about a point in the training set, which we really maybe shouldn't have had been able to predict, well, convince yourself that the privacy violation was not really the fact that we predicted that y equals pi plus 1, given that x is equal to pi, but the privacy was really relinquished. It was given up as soon as it was announced that the point in the training data had x is equal to pi. Once you knew that, then you sort of know the other private information, the rest of the information about the data point. So while this example might seem kind of silly, if you fully understood all the implications of what we just discussed, you are now prepared to judge whether or not something is a privacy violation. Now, for the rest of today's lecture, we're just going to go over many examples talking about what is and what is not a privacy violation. So let's instantiate a similar type of setting with an example that we've already seen before. And that's going to be the smoking causes cancer example, which everyone loves as a example of what differential privacy isn't supposed to protect against. So recall the setting. Suppose you're an individual who smokes and you're weighing whether or not to participate in a study which tests the hypothesis that smoking causes cancer. You would be averse to this hypothesis becoming public, that smoking causes cancer, because that would lead to your insurance premiums rising. Indeed, you smoke, so therefore they might predict that you're more likely to get cancer, and therefore they can get away with charging you more for insurance. However, this is very similar to the above example. Instead of the classifier here being y equals x plus 1, the classifier would be if an individual smokes, they are likely to get cancer. Similarly, instead of the point being pi plus 1, the point would be the feature vector. The feature vector would be the single feature that you smoke, and the label would be that you are likely to get cancer. So if you just sort of consider that mapping, this is essentially exactly the same setting we were in before. Indeed, whether or not one actually participated in the study, it would have been likely to arrive at the exact same outcome. And the only way to prevent this would have been not to run the study at all, say not ever investigate this fact. But in some sense, it's a fact about nature, and it's not really, this is not considered to be a privacy violation. In particular, in this case, you kind of gave up your right to privacy as soon as you disclosed your status as a smoker. Anything that's derived from that, which just uses nature as a result, and patterns in nature, would just be corollaries of that. Privacy was something you gave up by revealing that you're a smoker. And let's take this to its logical extreme, borrowing an example due to Frank McSherry. I don't even want to focus on this sort of little bit of a red herring with this experiment. It simply obfuscates the point. Let's suppose you see someone wearing a cast on their foot, a sort of white cast which covers it. And you don't really know for sure anything here, but it's very easy to infer, given the fact that they're wearing a cast on their foot, that they probably have a broken foot. So the former thing is something which is something they sort of wear on their sleeve, so to speak. It's something that they show in public. But it allows you to infer something which is potentially something they might consider private information. Even if you consider the latter to be sensitive information, by giving the fact by revealing the fact that they wear a cast, this is kind of giving up their right to privacy here in some sense. So whatever you can infer from the former will give you the latter. And that's not a privacy violation. So one can, in particular, just sort of talking about when was privacy given up again, as soon as they wore a cast, that's when privacy was given up. So these are very basic examples. Let's talk about some slightly more sophisticated examples, things which might seem to you like things where something went wrong, someone's privacy was violated. And in fact, often these types of results are marketed as such, but for reasons we'll discuss, and we have discussed already, in fact, we're not really going to consider these privacy violations because there's something which is unexpected. It might be creepy, but really your data wasn't really treated unfairly. It's just that it happens to be that nature is kind of working against you in some sense. So let's go over a couple of examples. The first one has to do with Facebook. So on Facebook, a user can like different pages, pages for various interests, and the set of pages which a user likes is by default public information. You can hide your likes and make sure that no one can see them, but by default they're public. And in 2013, a study came out by Kosinski, Stilwell, and Grapel, which showed that based on an individual set of likes, it was possible to infer sensitive information, including rather sensitive topics such as the user's sexuality or political affiliation. To provide you with some odd and perhaps unexpected correlations of other things they could predict, one thing they found out was some of the signals which were most correlated or most indicative of the individual being a high IQ individual were things like enjoying the Colbert Report, or enjoying liking the page for science, or perhaps surprisingly liking the page for curly fries. And so this is the kind of inference that one can make. You might think that just by seeing that an individual likes curly fries, you might think, okay, that doesn't really tell you much. But in fact, their studies showed that this is a pretty good sign that someone's a high IQ individual, which is more than a bit surprising, I think, to me. And this is a fairly innocuous correlation, but there were other ones which would reveal more sensitive characteristics, including sexuality or political affiliation. So they in fact included the word privacy even in the title of their paper. However, this is not really something that we would consider a privacy violation, and kind of for the same reason as before. So while their analysis was not run with differential privacy, presumably the results would still hold even if you did run them with differential privacy. Regardless, this is a bit of a red herring. Why is that? There's not really much private data here, in the sense that most of the data they used, that is the set of Facebook likes, that was public information. People had kind of freely given that up. Anyone in the world could look at this data and do whatever analysis they want on it. Of course, there are some sensitive topics that they used. For example, they collected people's sexuality as well as their political affiliation. But this is something that some people offer up themselves. For example, some people who publicly indicate that their sexuality on their Facebook profile, this would correspond to a labeled data point. And from these labeled data points, one could similarly infer perhaps not quite as good quality data, but they would still be able to infer these sort of relationships between individuals' likes as well as based on their set of likes, they would be able to infer their sensitive attributes. So the kind of tricky part here is like, how can a learning algorithm fail to protect privacy if there is in fact no sensitive data set at all, in the sense that all the information is freely given up publicly? So yeah, this is really just machine learning in action here. So yeah, really, when was privacy given up in this situation? Privacy was given up as soon as you chose to publicly reveal the pages you like, which again is a default, but as soon as you started liking things and revealing this publicly, that is sort of when privacy was relinquished. Even if you don't consider this information by itself to be sensitive, it serves as it may serve as a proxy for information which you do consider to be sensitive. So one interesting feature here is the fact that, privacy can be kind of given up even before the fact. Let me rephrase that. In fact, you might reveal a fact about yourself which you don't think is sensitive. You don't think it's really anything too private, nothing that you're afraid to share. But it might be that after the fact that this is actually sensitive and something you didn't want to share. So for example, before this study came out, you might just freely release all of your likes on Facebook publicly because you think, okay, I'm not going to like anything that's too incriminating. Well, what the study kind of shows is that even if you release this information after the fact, it's still possible for what you thought was okay to be released to come back and bite you. But nonetheless, just to recollect, there's not really any sensitive data set here. Everything is sort of all the data was released publicly, so we don't really consider this to be a privacy violation in a sort of individual privacy sense. Okay, as one last example of what is not a privacy violation, we'll talk about another example which is a little bit apocryphal. There's some doubts regarding its authenticity. People aren't really sure whether this happened or not, but the story goes around a lot. So take it with a grain of salt. But nonetheless, if the story were to be true in truth, it still wouldn't really be a privacy violation. So the store Target is well known for doing targeted marketing in the sense that, it sends targeted mail to its customers. Based on the things you've bought in the past, it can predict what you'd be interested in purchasing next. For example, you buy a certain brand of toothpaste and you do this again and again, then maybe it figures you like this toothpaste and maybe it'll offer you a discount to get you to buy it again. So this kind of targeted marketing can have some interesting side effects, hypothetically. And the one sort of story which goes around a lot is that one young woman in high school was said to have been sent an unusual amount of advertising pertaining to babies and motherhoods. Think like, a crib and maternity wear and stuff like that. But this really upset her parents because, she's in high school. Why is she being sent all of this? Is not really relevant to her. And kind of is kind of weird to be sending that to a high schooler girl. However, as the story goes, it was later revealed that this woman was in fact pregnant, and Target had managed to infer this prior to her parents based on her past purchasing habits. In particular, perhaps she had bought certain things which were not at all even seemingly related to pregnancy. Maybe a pregnancy test might be an obvious thing, but other sorts of things like certain brands of, I think, skin lotions are said to have been correlated. And certain anti-nausea pills. Stuff like this, which are seemingly indicators of being pregnant. So again, it feels especially creepy, and it feels like really something went wrong here. But the thing is that Target's data analysis was not really the failure of privacy here. The failure of privacy here was when the woman provided her purchase information, which is linked to her identity, to Target. To avoid something like this, the right strategy would be perhaps to give up on these consumer loyalty programs and instead just buy things sort of anonymously. So in short, the story is indeed creepy, but it is not an instance of Target performing a privacy violation. So at this point, I think we've belabored enough what are not privacy violations. You might be even forgetting what is a privacy violation at this point. So we've actually, remember, if you think back to the first lecture, we talked about this more than a few times, and we're going to reinspect some of the instances we've already discussed. There's two examples. One, first of all, the Netflix prize. Let's recall what exactly this is. Netflix, they released an anonymized version of their users' data history, their users' view history. That is, for a set of users, they released what date the movie was watched, what score the user gave the movie, and sort of an anonymous user ID, which doesn't reveal their name, but it just sort of is an identifier to say who the user is. But Narayanan and Shmatikov linked these records with public IMDb data. That is, users went on IMDb and recorded what movies they watched and what they reviewed and stuff like that. So this linkage between the public IMDb data, which we do not consider to be sensitive because the users freely offered this up, was able to be cross-referenced and linked with the Netflix data, which was in fact sensitive, and they were able to discover movies the users had watched, which they had not previously disclosed publicly. So this is indeed a privacy violation, and the privacy violation here was Netflix's faulty anonymization of the data, which revealed sensitive information about individual users. In particular, let's see why this is. In particular, if a specific user's data was withheld and it was not actually in the data set, then the same re-identification would not be possible. This is a fundamental difference between the setting and all the other ones. The user was kind of harmed by opting into this type of analysis, and you were able to identify things based on the data that they considered sensitive. So somehow their privacy was not respected. The privacy attack was in fact contingent on the individual sensitive data. Those movies which they watched but they didn't review on IMDb, those were in the data set, and that's and those were revealed. So just by comparison, let's consider by comparison another very, very similar setting where in fact there was no Netflix data set, there was no Netflix anything here, where an analyst just looks at the movies that an individual watched on IMDb and what they publicly released that they're happy to announce to the world that they said they watched. Well, an analyst could also do an inference on what other movies that they watched as well. For example, suppose a user reviewed Rush Hour 1 and Rush Hour 3. From this, it seems pretty likely that you can infer they watched Rush Hour 2. So this is not considered to be a privacy violation because all the inference we did was based on what they publicly released, as well as, perhaps what nature suggests. For example, if they're into action movies, you might infer from this that maybe they also watch, say, Die Hard movies, other type of action movies. Even if this type of prediction you do based purely on their public data happened to be perfectly accurate, it wouldn't be a privacy violation because there's really no sensitive data set here. Everything was offered up freely. If anything, privacy was really given up when users chose to reveal parts of their viewing history. So as one final example for this lecture, let's talk about The Secret Share by Carlini et al. This was the one involving the language model back in the first lecture that we talked about, where in this setting, a language model is trained on some sort of sensitive data set. In particular, the model is once you have this trained model, it can be given a sequence of characters as input and will output a log perplexity score for the sequence. Roughly speaking, to recall, a lower log perplexity score corresponds to a higher probability of the sequence. And what did we see in this setting? In this setting, in their investigations, we saw that if an individual repeatedly used a single phrase that was unique to them, so they kept saying a specific phrase. For example, suppose they used their social security number repeatedly. Then the model would be prone to memorizing and in fact could be coerced into revealing the secret phrase just via the right sequence of queries. This is again a privacy violation indeed, because it appears the model has overfit to a particular individual's data. And in fact, the answer would change significantly if their data were left out. Recalling the example, just think about the setting. Imagine you had a perfectly accurate model of English that is admittedly underdefined, but suppose there was the algorithm output a perfectly trained language model which got 100% accuracy on English, whatever that means. It could truly speak English. Then it would really have no reason to assign significantly higher probability to an individual social security number rather than any other number of the same format. So therefore, this isn't really what we consider as a privacy violation, since or sorry, this is what we consider to be a privacy violation because of the fact that, it kind of depends very, very heavily on the fact that you're working on their private data. But at the same time, if you trained a perfectly accurate language model, which is perfect for English, then this wouldn't be a privacy violation. So indeed, we've discussed in detail several examples of what is and what is not a privacy violation. This can again be a very tricky topic to get right, but you should be in good shape if you just keep asking yourself the questions which were outlined at the start of the lecture. In particular, the key question in my mind is always asking, is this a privacy violation, or is this just statistics and machine learning doing what they're supposed to? It's often one or the other. And in particular, if it's both at the same time, you're saying it is a privacy violation and machine learning is doing what it's supposed to do, then in fact, it seems likely that your notion of what a privacy violation is might need a little bit more consideration. So that's it for today's lecture. In the following lectures, we will see how to prevent privacy attacks using differential privacy in machine learning settings.